So in the last class, we talked about or introduced the concept of K-maps, the Karnaugh map, and we have also seen that the K-map is nothing but using the Boolean identities in a more systematic manner. That's all it is. Okay, there's nothing new. A K-map is a more uh, compact representation of your truth table. It conveys the exact same information, and it makes combinations, makes applying the Boolean identities in a much more faster and efficient manner. Okay, so if you do the right thing, if you do the right, if you exactly follow the rules of the K-map, you will always end up with the simplest function. Okay, unlike in Boolean simplification, where you use the identities and then you end up with an expression and you don't know if that is the simplest expression. Could it be simplified further? Am I missing any identity there? You don't have the problem with K-maps. It basically gives you the simplest function as long as you use the right rules. Okay, as long as you follow the right rules. Okay, so the rules are, again, basically you draw the K-map based on the inputs. Let's say f of a, b, c, d is my function. That means here I have 4 input function. Okay, my K-map should have number of cells. My number of cells in the K-map should be equal to the number of minterms. That means in this case, for example, if I have a function with 4 variables, I would have the number of cells equal to 16. Here it's 16. Okay. So that's the first step. Now, the second step is, again, remember that each cell represents a minterm, because each cell represents a minterm. And in the last class, we discussed the concept of adjacency, right? Two cells are adjacent. When I go from one cell to the next cell, only one variable change occurs. Okay, and to make physically adjacent cells to be adjacent according to this rule that I just described, sometimes it may be essential to swap the position of the minterms. And this is what we have done in the last class, right? And exactly the same way in this case, we have to draw the K-map and position the minterms so that physically adjacent cells are indeed adjacent according to the definition. And we will be doing that in this to illustrate that concept. Okay. All right. What else do we need? So now, once you draw the K-map and your cells and so on, okay, when to label them, the next step is you place ones. Again, that depends on the function, because your function is given. Your function can be something based on, typically that's given in terms of minterms. Place ones in the cells for which the function is true. Function is true because each cell contains the minterm. Your K-map itself is a compact representation of the truth table, so it follows that I place ones in those minterm positions or in those cells for which my function is true. The third step is, now you combine adjacent cells. Again, I will be combining them based on one adjacent cell or one cell. In this case, you could have a cell that is isolated. I cannot combine them, combine that cell with any other cell. So I would basically, keep it. I would combine it as itself. Okay, and then I can combine two adjacent cells. Now, if you remember, the larger the combination, the more number of variables I'll be eliminating from my expression. Okay. Now remember, so combine adjacent cells, one adjacent cell, two adjacent cell, or 4 adjacent cells, and so on. So again, the concept is we'll be combining in terms of 2 power n adjacent cells. So that's the idea.
So, as we mentioned last time, it can be 6 adjacent cells.
It cannot be 6 adjacent cells. It has to be power of 2. So 6, you cannot express 6 as a power of 2, so you cannot combine 6 adjacent cells or 3 adjacent cells. It has, because again, It's based on symmetry, right? That we have described in the last class. So it has to be in terms of power of 2. Okay. I would always go for the largest combination. Why do I want to do that? Because again, remember that these combinations produces a product term. Each combination gives you a product term. These product terms, the function is basically a summation of those product terms. Now, when I combine once I go for highest possible combination, okay, I'll be eliminating more variables. The idea here is if I combine one adjacent cell or one cell, there is no variables eliminated. Two adjacent cells, I'll be eliminating one variable. Four adjacent cells, I'll be eliminating two variables from my product term. 2 power n adjacent cells, I'll be eliminating n variables from my product term. Okay, so the larger the combination, more number of variables I am eliminating from my product term. So my goal is to always go for the largest possible combination. Okay. Now, if you don't go for the largest possible combination, whatever function you get in the end is not going to be the most simplified function. So that's something that you need to remember. That means it can be simplified further because you have not chosen the largest possible combination. Okay, so that's the idea here. And most importantly, you need to account for all the ones. Make sure that every one in your K-map is accounted for, because you know that one forms one is part of your function, right? So you account for all the ones in the K-map. Okay. Even if that, even if I have to account for a particular one with a single combination of adjacent cell, that is also fine as long as you account for all the ones. Then you're not really changing the value of the function. Okay. So that's the idea here. So that's what we have discussed in the last class. Now let's take an example and put these things to practice. Okay, this time let's actually look at the example of a 4-input K-map. Okay. All right, so let's do that. In this case, my function is this is a 4-input function where my A, B, C, and D are the inputs. So I have 0, 2, 3, 7, 11, 13, 14, and 15. So these are my minterms, or my function is expressed in the form of minterm position for which my function is true. Now let me draw the K-map corresponding to this 4-input K function. Again, 4 inputs, that means I have 16 minterms. That means my K-map, when I draw the K-map, that should contain 16 cells. Right. All right, so let's do that. So that's my A and B, C and D. Okay. So that's how my A and B varies. 0, 0, 0, 1, 1, 1, 1, 0. Again, we remember the swap here. I'm trying to make sure that physically adjacent cells that are next to each other are adjacent according to the rule, where I go from one cell to the next, I have only one variable change occurring. Likewise here, I have 0, 0, 0, 1, 1, 1, and 1, 0. Now let me number the minterms. You can number the minterms based on the binary value here. So for this particular minterm, for this particular cell, you can see the binary value corresponding to that is 0, 0, 0, 0, which is 0. Right? So I can just number this here, that's 0. Minterm corresponding to that would be 0, 0, 0, 1, that's 1. 0, 0, 1, 1, that is 3. 0, 0, 1, 0, that is 2. In this case, 0, 1, 0, 0, that will be 4, 5, 6, 7. And then this will be 8, 9, 10, 11, 12, 13, 14, 15. So that's the standard format. Okay, you'll always draw your K-map for a 4-cell, 4-input K-map. I would always draw this in this format: 0, 0, 0, 1, 1, 1, 1, 0. That's the swap here. That's the swap here, again, to make sure that my physically adjacent cells are next to each other, or adjacent to each other, according to the rule. Okay, so that's good. So we have done with that. Okay, now before we put the ones, so according to the process flow, I draw the K-map. Okay, I have that. The next thing that I'm supposed to do is place ones in the cells for which my function is true, and that is given by these positions or the minterms. I can do that. But before we do that, let me ask you which cells are adjacent, or let me put it this way. By making this swap, I ensure that these two cells are adjacent to each other. These two cells are adjacent, these two cells are adjacent, these two cells are adjacent, these two, and so on. The physically adjacent cells are adjacent according to the rule. Now, beyond those physically adjacent cells, do you see any other cells that are adjacent to each other, that may not be touching each other, that may not be physically adjacent, but are adjacent according to the rule that we mentioned? Okay.
0 to 8, 10, 2,
Okay.
10, 0, 8,
All right. So
6,
let me
4.
put that down. So 0, 2. Yes. This cell is adjacent to this cell.
Yep.
Why? Because again, the minterm corresponding to that is A prime, B prime, C prime, D prime here. Here I have A prime, B prime, C, D prime. So the only thing that changes going from this cell to this cell is C, right? C changes from 0 to 1. Every other term remains the same. So yes, 0 and 2 are adjacent. Let's see, what else do I have?
Isn't that a D? No?
Sorry?
The D changes, right?
The D from here to here, D remains
No,
0,
D.
right?
The D changes, right? On that part, 0 to 2 is
The D
Oh,
remains the
I see
same.
now. Oh, yeah, yeah, okay, okay, my bad.
Again, remember, this corresponds to D, this corresponds to C, right? The way I've written here. C comes first, D comes
Okay.
next. So this 1 corresponds to C, this 0 corresponds to D. So D doesn't change, C changes. Okay.
Okay, thank you.
And 0, 2, 4, 6, let's see. 4 and 6, yes, 4 and 6 are adjacent to each other by the same token. 12 and 14, let's see, 12 and 14, that's correct. Likewise, 8 and 10, that's correct.
So it could
Or
be 412. It's adjacent to 614, right?
412 is adjacent
412,
to, yes, that's correct.
614.
Yes. So in other words, in other words, this entire row is adjacent to this entire row. If I have ones in this entire column, ones in this entire column, I can combine them into a combination of 8 adjacent cells. Okay. Likewise, if I have ones on my corners, remember that this cell is adjacent to this cell, this cell is adjacent to this cell, this cell is adjacent to this cell, this cell is adjacent to this cell. So this, I can combine them, even though they're not physically touching each other. I can combine them into a single combination, something like that. That's into a single combination of 4 adjacent cells. Just like, so this is equivalent to saying, if I had these, so these ones in these cells, I could have combined them into a single combination. So this combination are equivalent. I mean, because it's the same thing. It's just that those ones are not touching each other because of the limitation in which, because we have, working with 2D diagram, you may have to, we just cannot express it as if they are touching each other. So we just combine them that way. Okay. All right. So I can combine these four cells as adjacent cells. So that's allowed. Likewise, 1 and 9 be adjacent to each other. 1 and 9. That's absolutely right. So if I had a 1 here and a 9 here, yes, I can combine them together as a single combination. That's 1 and 9 are adjacent to each other. That's absolutely right. So in other words, you can actually fold them into a three-dimensional spherical shape to make them touching each other, I guess. But yes. So your columns, this column is adjacent to this column. This row is adjacent to this row. All right. So with that, let's actually start doing this problem now. Let's actually do this. It may be better to just start a new one. Okay. So I have A, B, C, and D. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Again, that's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay. Now let's place ones in the cells corresponding to these min-term positions. So I have one here, I have one here, one here, one here. 11 is, that's fine. 14, 13, and 15. So that's the K-map corresponding to that function. Okay, that's the K-map corresponding to that function. Now I would like to combine adjacent cells to the largest possible combination. Okay. Okay, let's do that then. Let's see. Do you see any possibilities here?
Of course, 2, 7, 15, 11.
2, 7, 15, 11. They are adjacent. This cell is adjacent to this cell. This cell is adjacent to this cell. This cell is adjacent to this cell. I have combination of 4 adjacent cells. 4 adjacent, I can combine them.
Yep.
So yes, I can combine them into a single combination. Okay. 2 and 3. 2 and 3, yes. These two cells are adjacent. I'm just looking to see if I can combine them into a larger combination. Looks like that's what it is. I can combine them into
Or 2, 0.
4. I don't have a 1 here. Do I have? No, I don't have any 1 here.
Let's say 2 and 0.
2 and 0. That's
0.
correct. I can combine them.
Yeah.
That's a good point. I can combine them. Okay. I still have to account for these two ones. 0, 2. That's fine. 15 and 14. Yes, I can combine them. Again, I would not be combining them into a single combination because that's not allowed. That's 3 cells. Symmetry is lost. Cannot combine them. So I can combine 14 and 15. That's allowed because that's 2 adjacent cells. I can combine them. And 13 and 15 as well. Now I have accounted for all the ones. Okay. And now it's time to write down the product term. All right. Now, this is a interesting combination here. Okay. Now, if I take this out, and I'm gonna, after this, I'm going to describe the actual technical terms for that. If I take this combination out, as you can see here, all my ones are still accounted for. I'm not really, as you can see here, because this one is accounted for this in this combination, and this one is accounted in this combination. So all the ones are already accounted for. So having this would not change the value of the function, but it's going to be tagging along as a redundant term. in the function. Not going to add any value to it. It's not going to change the value of the function, but it's at the same time, it's not going to add any new value to it. So having that or not would not change the value, so I might not, I will not have it, right? So that's a non-essential term, if you will. So that's a non-essential term. Okay, now let's start writing the product terms, because each combination eventually produces a product term, right? Which you can read out by eliminating the variables that change, keeping the variables that do not change. So let me number them. So let me call this 1, let me call this 2, let me call this 3, and let me call this 4. Okay, so now what will be 1? Again, this cell is combined with this cell, right? Again, going from this adjacent this cell to this cell, what are the variables that have changed? Again, remember that this min term corresponding to this cell would be a prime, b prime, c prime, d prime. Min term corresponding to that cell will be a prime, b prime, c, d prime. So c is the one that changes from 0 to 1. What remains is a prime, b prime, d prime, right? So that's going to be the product term that I end up with for this combination will be a prime, b prime, d prime. Okay. What is 2? So what about 2? 2 is a combination of these two adjacent cells. All right. Now here, as you can see, A and B remains as AB. Going from this cell to this cell, my AB remains as AB. What changes? And then C also remains as C. What changes is D, that changing from D to D prime. Going from this cell to this cell, D changes as D to D prime. So my 2 will be A, B, C, right? A, B, C. 3 would be this combination. Again, my A and B doesn't change when I go from here to here. A and B remain as AB. What changes in this case is C changing from 0 to 1. What remains is D remaining as D. So that's going to be A, B, D. And finally, the fourth combination. In this case, again, C, when I go down this column, C and D doesn't change. They remain as C, D. My A and B values change, right? 0 for A and B range from 0 to 0, all the values. So A and B values change as they go across down this column. So those get eliminated. What doesn't change is CD, so that's going to be CD. So my function in the end, my simplified function would read as A prime, B prime, D prime plus ABC plus ABD plus CD. And that's the simplified function. Cannot, because I've used the rules, it doesn't matter. Okay, so that's a good point. Again, because my Boolean algebra, in this we have the commutative law, which says x plus y is the same as y plus x. The order of operation, order of placing these variables really doesn't change the value of the function. So I can place them in any order. That should be fine. Okay. All right. Any questions on that? Okay. If you don't have any questions, then let's start defining the actual. I'm using the term largest combination and then non-essential terms and essential terms. So let me actually give them a more formal technical terms and definitions for those. Okay. Now, so let's start with what is called the prime implicant to start with. Okay. So what I've been calling so far as the largest combination, that would correspond to prime implicant. Okay. So your prime implicant prime implicant, that would correspond to the largest possible combination of adjacent ones. Okay, that's basically the largest possible combination of adjacent ones. Of course, this has to be in terms of 2 power n combinations, 2 power n, okay? Combination of adjacent ones, okay? That's your prime implicant. So all of these that we have combined here, each one of them will be a prime implicant. Okay? What will not be a prime implicant would be a combination that corresponds to this combination. For example, if I come back and say, combine these, because these two cells are adjacent, if I combine them, if I combine these two cells, those cells are not, those combinations are not called prime implicants because I could have combined them into a larger combination. That's not the largest combination. Combining these two cells, when I have additional adjacent cells, those will not be called the prime implicant. Okay? So they'll be called just the implicant, if you will. Okay. All right. So that will be the prime implicant for this combination. For this combination, that will be the prime implicant. So these are all prime implicants. Okay. All right. So that's your prime implicant. Then we have what is called the essential prime implicant. So let me define what is called the essential prime implicant. Now, of course, first of all, it has to be a prime implicant to start with, and it has to be essential implicant to start with. That means it has to be the largest possible combination. All right. And then what makes a prime implicant essential is that it should contain at least one cell that is not accounted more than once in any other combination. Okay. Now, in this case, if I were to draw all possible prime implicants, then this would also be a prime implicant. I could have combined this one with that one. That's a valid combination. That's the largest combination I can combine, and that's the prime implicant. Okay. Now, coming to the essential prime implicant, there should be at least one cell. It should be a prime implicant. There should be at least one cell in the combination. Okay. At least one cell in the combination not accounted more than once in any other combination, in any other combination. So that's called the essential prime implicant. Okay, so let's see what are the essential prime implicants in this example. Now, if I go by this definition, would this prime implicant be called an essential prime implicant? I have two ones in that prime implicant, or two cells in the prime implicant. Okay, you notice that this particular cell containing one is accounted in this prime implicant combination as well as in this prime implicant combination, right? And this particular cell is accounted for in this prime implicant combination as well as in this prime implicant combination. So in this particular prime implicant, I don't have at least one cell that is only accounted for one time. In this case, both the cells are accounted more than once. So I would call this a non-essential prime implicant. This is not an essential prime. So this is called the non-essential prime implicant. It's a non-essential prime implicant. Okay. Now what about this particular combination? Where I have this and this combined. Now this particular cell is accounted more than once in this combination as well as in this combination. but this particular cell is only accounted once, right? It's not accounted in any other combination. So this particular cell is only accounted once. So I would call this the I will call this the essential prime implicant. Okay. And likewise, I can check for every other prime implicant. What about 3? The prime implicant 3, which is this one. I see that this particular cell is accounted more than once. This combination, right? However, I have at least one cell, which is this one, the cell number 13, that is only accounted for one time, not more than one time. So I would call this also as an essential prime implicant. Okay. 4, I have multiple cells that are not accounted more than once. So for example, this cell is not accounted more than once. This cell is not accounted more than once. So of course, my 4 is also essential prime implicant. So that's how I can classify my prime implicants as essential prime implicants and non-essential prime implicants. And when it's time to write my function down, I would write my function f as sum of essential prime implicants. So your essential prime implicants are always going to be there, plus some non-essential prime implicants. You don't choose all of them, you choose some of them, so that all the ones in the K-map are accounted for. So the ultimate goal is again to make sure that when you do this K-map, every single one in the K-map has to be accounted for in one or the other combination. So by choosing this, by writing down this function as sum of essential prime implicants, plus choose some of those, not all, but some of the non-essential prime implicants, so that all of them are accounted for. So in this case, as a matter of fact, I don't even have to choose this non-essential prime implicant, because even not choosing this, I can ensure that all my cells are accounted for in this case. That makes sense? Yeah, Samuel.
So the non-essential prime implicants don't really matter as long as we can cover every one. The function should
Yes,
be correct.
that is absolutely right. So sometimes you may have to use it, but in this example, I don't have to use this. I can just take it out, because even by taking this out, I have accounted for all the other ones. All the ones are accounted for just by using the essential prime implicants. So I don't have to use that. Let's take another example where I have to use some of the non-essential prime implicants. Okay. But before we move on, any other questions here? Does it make sense, the concept itself? So this is required, and this is kind of, depending on the situation, that can be optional. In this case, it's definitely optional. I don't have to use any non-essential prime implicants here in this particular example. But there are situations where we may have to use some non-essential prime implicants so that I account for all the ones. All right, so let's take another example. Hopefully that will make things clear. So what do you think? When I'm trying to simplify a function, okay, I'm trying to obtain a function for a particular functionality. So the simplified function, would I always have a unique function, or could be different? What do you think? When I simplify a function, okay, are there instances where I can have multiple instances of the simplified function, or I will always end up with a unique solution, unique function as a simplified function? What is your guess? Meantime, let me put down the problem. And this particular question would answer that. here's the problem, which is given A, B, again a 4-input function given as sigma m 0, 2, 3, 5, 7, 8, 9, 10, 11, 13, 15. Okay, so that's the given function. Let's draw the K-map corresponding to that. Again, that's a 4-input K-map, so I have 16 cells. Let's do that. Okay, then put down the numbers. You'll see that once you get used to working with K-maps, after a while you don't even have to put down the numbers. You can directly write down those runs in the corresponding cells. But now let me put down the numbers anyway. Those are the midterm positions: 4, 5, 6, 7. Okay. Now let me put down the ones. In this case, I have 1 corresponding to this position, 2, 3, 5, 6. No, there's no 6. 7, 8, 9, 10, 11, 13, 15. So I have a K-map that looks something like this. And now I would like to look at all prime implicants. Could be essential, non-essential, doesn't matter. At this time, I would like to look at all possible prime implicant, the largest possible combination of adjacent ones. Any clues here? Do you see any adjacent ones, any combinations?
8, 9, 11, 10.
Okay, 8, 9, 11, 10. Yeah, that's a combination of 4 adjacent cells. I can combine them.
5, 7, 13, 15.
5, 7, 13, 15. Absolutely. I can combine them.
3, 2, and other one is a 2, 0.
Sorry?
3, 2.
Okay, that's a good point. 3, 2, is that going to be a prime implicant?
Not sure.
0, 2, 8, 10. Okay. 3, 2. They are adjacent. If I combine them, I would that would not be a prime implicant in this case, because I have 2 additional cells here that these 2 cells can be combined with. Do you see that? This cell is adjacent to this cell. This cell is adjacent to this cell. These 2 cells are adjacent to each other. These 2 cells are adjacent to each other. So I can combine these 2 cells and these 2 cells together to form a combination of 4 adjacent cells. Do you see that?
Yep.
So in this case, 3, 2 would not be a prime implicant, but I can combine them into a larger combination. So let me put it that way. Okay. So that will be a prime implicant in this case. And finally, I have the corner cell, because I have this one and adjacent to this cell, adjacent to this cell, this one is adjacent to this cell. I can combine them into a combination of 4 adjacent cells. All right. Are you with me until this point? Okay. Now, do you see any additional combination? Now, if I were not asked to list out all possible combinations, as in if I were not asked to list out all prime implicants in this case, I'll be done with this problem. That's it. I would, I've accounted for all the ones. I would write down the product term corresponding to each prime implicant, and I'm done. Okay. But if I were to ask for all possible combinations, all possible prime implicants, then I have to look for additional combinations. So let's see. So you have 3, 7, 15, 11. 3, 7, 15, 11. Yes, that will be a combination. So let me combine them. I'll use a different color for that, so we're not too confused. All right, so that's right. Any other combinations? Do you see any other combinations?
13, 15, 9, and 11.
13, 15, and 11. Yes, absolutely. That's also a prime implicant. All right. Any other possibilities? 2 and 0. 2 and 0 will not be a prime implicant. Oh, well, it's not be a prime implicant because I already combined. I've already obtained a larger combination, right? So that will be the prime implicant. If I combine just 2 and 0, that will not be a prime implicant. So here I want to combine only the prime implicants, which would be the largest possible combination of adjacent ones. Looks like that's it. Now let's number them. Let me call this 1. Okay. Which is a combination of the corner cells. Then let me call this to be 2, second prime implicant. Let me call the column 1 to be 3. Let me call this 4. Let me call this 5. And that's it, right? Looks like, yeah. Okay, now I would like to identify which ones among those are essential prime implicants. The bottom, okay. Oh, yes, that's correct. And I have 6. Okay, so I have 6 prime implicants. And now I would like to basically identify from among those combinations which ones are essential and which ones are non-essential. Okay. All right. Which ones are essential? Let's start with 1. Is 1 an essential prime implicant? Again, 1 corresponds to these corner cells. 1 is an essential prime implicant, that's correct, because I have at least one cell, in this case, this particular cell, that is only accounted once in the combination, right? So that corresponds to an essential prime implicant. What about 2? 2 would be this combination. 2 will be a non-essential prime because I don't have any cells that are not accounted just once. Okay, what about 3? 3 would be the column 1. 3 is also no, so that's a non-essential prime as well. Let me see, 4. 4 would be this one. 4 would be a yes, because I have at least one cell that is not accounted more than once. That will be an essential prime. 5. 5 would be that. And that's going to be a non-essential prime as well. I don't see any cell that is not accounted more than once. I don't see any cell that is accounted only once. So that's going to be a non-essential prime. And finally, we have 6. 6 is also non-essential prime. for the same reason. 6 is this. I see all the cells are counted more than once. That's definitely not an essential prime. So this is my classification of my prime implicants and non-essential prime implicants. Let's write down the product terms as well. Okay, what would one correspond to? So we want to write the product term. One is again the corner cells. Again, I go from one cell to the next, or across those combinations. What are the variables that do not change? I'm going to write down those variables and eliminate the variables that do change. So when I go from here to here, okay, A and B remain as A prime, B prime, but C changes from 0 to 1, B remains as 0. So that's going to be, and then, so that's, when I go from here to here, C gets eliminated. And when I go from this cell, adjacent cell, to this adjacent cell, what gets eliminated? Again, 0, 0 here, 1, 0 here. A changes, B remains as B prime. So the variable that do not change across this combination of 4 corner cells is going to be B prime and D prime. Right? When I go from here to here, C gets changed. Yeah, B prime and D prime. That's correct. What about 2? 2 would be this combination and this combination. Again, when I go from here to here, I can see that A changes from A prime to A, B remains as B prime. So B prime is going to be there. And when I go across from this adjacent cell to this adjacent cell, so I'm always going both vertically as well as horizontally to see which ones are remaining, which ones are changing, and I eliminate the ones that change, keep the ones that do not change. So when I go from this adjacent cell to this adjacent cells, I have C remaining as C, D changes from D to D prime, so C remains as C, so that's B prime C. Okay. Third is this column. Obviously, when I go down, A and B changes, A and B gets eliminated. What remains is CD. Those are the ones that do not change as they go from one cell to the next cell. Okay. 1, 2, 3, 4. Product term corresponding to 4, which is this particular combination. Again, I go both horizontally as well as vertically across the adjacent cells. So when I go vertically from this adjacent cell to this adjacent cell, I see that A changes, B remains as B. When I go horizontally from this adjacent cell to this adjacent cell, C changes, D remains as D. So that's PD. 5 would be this combination. Again, when I go vertically, 1, 1 to 1, 0, B changes, A remains as A. When I go horizontally from this adjacent cell to this adjacent cell, C changes, D remains as D. That's it. And finally, 6, that's going to be the row. Again, of course, when I go across horizontally, adjacent from one cell to the next, my C and D gets eliminated. The one that does not change are the A and B, which remains as A, B prime. Okay. So those are my product terms corresponding to my prime implicants. And now it's time to choose my function, to write down my function. In how many different ways I can write down my function? Okay. All right, so let's do that. Now, again, I can write down my function as a sum of the essential primes. So these are going to be common terms in every possible combination of the function, every possible version of the function. And then I choose the non-essential primes to sort of, account for all the ones in the K-map. I will not be choosing all of them. I'll be choosing some of them to account for all the ones. Okay. Now, what are the essential primes again? So in this case, my essential primes are 1 and 4. 1. So let me do one thing. I will change this color. That's 1, right? To indicate that these are accounted for in my essential primes. So that's 1, 1, 1, 1. Okay. So those are accounted for in my essential primes. And I have also 4, 4. So let me change the color for that as well. One, 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 one. All right. So write this as 1 plus 4. Those are my essential primes. And I'll choose those non-essential primes because I still have to account for how many ones? 1, 2, 3. I still have to account for 3 ones. I'll choose some non-essential primes to account for those 3 ones. So one possible way is to account for this particular one. Let me choose, this non-essential prime implicant, which is 3. Second, one of the possibilities would be 3, in which case these 2 ones are accounted for. I still have to account for this one, and I can account for that using this combination, which is 6. So that's one possibility. Do you see that? That's one of the ways of expressing the function. As you can see, I have not chosen in this particular function representation, I have not chosen, or I don't have to choose about 3 and 4, 6, right? 3 and 6. I did not have to choose 2. That's a non-essential prime. That's not going to change anything. Or I don't have to choose 5. I'm okay with that. So that's one possibility. What is the other possibility? Again, for every possibility, my essential primes has to be common because they are essential primes. I cannot, have them without it. Plus, I'll choose a different combination of non-essential primes this time. Okay, what can I do now? What are the other possibilities now? Do you see any other possibilities? This is one possibility. Do you see any other possibilities there that I can choose to get my simplest function? Okay, 2 and 5. So 1 and 4. So 2 would be what? 2 would be that one. So when I choose this, these 2 ones are accounted for. So yes, 2, I can choose 2. Now I still have to account for this particular one, and I can account that in 5. Yes, absolutely, that's right. So that's also that's the second possibility. And that's it, I'm done with that. Any other possibilities here you can think of? So I have 2 possibilities for the simplest function. So as you can see here, my function, the simplified function, does not have to be unique. There are instances where I can have multiple versions of the simplified function, completely looking different, and yet producing the exact same effect, same functionality. All right. Any other possibility here? 2 and 6. Okay, so my function, that's going to be the third possibility where I have 1 plus 4 plus 2 and 6. 2 and 6. Let's see if that works out. So 1 plus 4, of course, I accounted for the red ones anyway through my essential primes. Now 2 would be that which accounts for these 2 green ones. And 6, what is 6? 6 would be that. No, that's not 6. Yeah, that's 6. Yeah, 2 and 6. That works. Very good. Any other possibilities or any other combinations? Three and 5. Okay, let me check. So 1 and 4. 4 plus 3 and 5 this time. Okay, so 3 would be that. Okay, that would account for these two ones. So 3 is fine. 5 would be that. Yep, that accounts for this one, and that's fine too. So as you can see, now I have 4 different possibilities. I don't think we can do any more than that, but I have 4 different possibilities that gives you the same function, exact same function, simplified function. And this kind of illustrates the concept of how we can express the function as a combination of essential primes and non-essential primes. All right, let me take a pause here and let me see if you have any questions about anything covered so far. Does that make sense? Okay, very good. All right, so if you don't have any questions, let me pause and stop this recording.